Okay, so hi everyone, Senan this side, and in this video we are going to see this wonderful problem which is known as the path sum. So what you would be given is this root of a binary tree, fine, and an integer target sum. So what do we have to do is return true if tree has a root to leaf path such that adding up all the values along the path equals target sum. Fine. Let's say in this case we have 22 as target sum. So if we add 5, 4, 11 and 2, that would give you 22. There might be other possible cases, but that is not the only solution. And let's see some more examples. Okay, so if root is this, that means there is no tree. The root is null and target sum is 0. So since there is no root, so there is no leaf node, so there is no path in the tree, and therefore we return false. But assume if we have target sum of 0, you can technically achieve this, but this question requires that there should exist at least one node in the tree. Now can we think of this recursively, right? So we would be writing a recursive algorithm, and let's see how can we break this question into a smaller question which we can actually solve. Okay, let's say first let's see, we have target sum of 12, so 5 plus 4 9 plus 11 is 20 plus 2 is 22, right? Okay, so if I start from 5, what do I know? That I have a value of 5 and I know what is the target sum, right? Now can we call the same function assuming this 4 as the root node and call the same function for the value target sum minus this root val or root value? So rather than calling the function on this with target sum 22, we would call it on 17. Fine. So now if I know we have to call this on 17, I can again create a sub problem saying that rather than calling on 17, call this on 17 minus 4 is what? 13, and on this node. And when I reach this root node, so I had 13, target sum is 13 in this node. By the time I reach here, I would have a target sum of 2. And since 7 is not equal to 2, I would say that this path is not leading us to a solution. Fine. This is the same logic, but since this returns false, maybe the other child of this node might have an answer. So we go and check this 2. So target sum is 2 and the root val is also 2. So yeah, if we add all these elements, technically we would have the target sum as 22. So basically we have discovered a recursive solution. Now for this we need to have a base case. Okay, so seeing example number 3, we know that if root is null, regardless of the target, we return false. So I'll say if root is equal to null, return false. Now what is the case 2? Case 2 is if the node that we are at is itself a leaf node. At this point we check that have we reached to a valid solution, right? So I would check if root dot left is equal to null and root dot right is equal to null. So that means we are at a leaf node. Okay, we are at a leaf node. What is a leaf? Leaf is a node which has no children, right? Now in this case we need to check if we have reached the target or not. So I would say if, or rather than return target sum equal to root val. So if we are at the root, so when we were seeing this example, if we were at 2 and the target sum was, in this case, was 2, so 2 is equal to 2, that means we have a valid path from root to leaf, right? So we would return this. Otherwise, we know that we are not at a root. So let's say for the sub problems, I would call int, let's say new target, and I would say that it is the target sum minus root val, right? This is what we are going to do, and I would just call the same function as path sum on root dot left with this new target. Similarly, I would call this on the right child as well, and if either of them is true, I would return true, otherwise I would return false. So I can just write this as return has path, and I can just do an OR in between. So this is our solution. I assume this is going to work, but let's just see what we are trying to do. So if either of them, let's say if we have a node which has only one child, either the left or the right. So let's say left child is null. So when we call this, using this case, we would return directly false, right? So then we go to check the right child, and after this if statement, we know for sure that the current node is not the leaf node. Then because of that, we need to have some recursive call in this. Now I can just rewrite this in a more neater format, and I can just write it like this. And if I just run this and just check if this is working or not. Okay, so accepted. All the cases are accepted. Let's just submit this and finish up with the video. Okay, so it is working very well. Okay, so what is the time and space complexity? So the time complexity, I would say, is that in the worst case, what we would be doing is we are traversing the whole tree and checking every route to leaf path, every possible route to leaf path. So first we started with 5, 4, 11, 7. Then we went to 2. If let's say if this was not 2 but 3, we would have traversed back, and then would have checked 8, 13. This would also not be working. Then 5, 8, 4, and 1. So this is also not a valid sequence. So in the worst possible case, what we would be doing is seeing each and every node, but that would be exactly once, right? So the time complexity would be big O of v meaning the number of vertices or the nodes in the tree case. And let's talk about the space complexity. And so the space complexity would be, let's say this is a recursive call, right? So 5 would call for 4, 4 would call for 11, 11 would call for 7, and then 2, right? So the space complexity, the recursion stack or the call stack would contain at max the maximum number or the max height of this binary tree. So that would be the space complexity. And yep, that's it. So the time complexity is number of nodes. We go of number of nodes. Space complexity is the height of the maximum height of this tree. So that was the video all about. Hope you found this useful. If yes, be sure to share it with someone that you might think would benefit them. And yeah, anyways, bye.